All right, so just below the Windows section, if you refresh this page, I've added these Rust projects, and I'll show you the highlights of this. So you can install it on Debian, sudo apt install Rust C for the Rust compiler, and then you can make simple Rust apps. Here's what it looks like. It looks a lot like C. You have a main function that prints a line saying Rust says hello. That's what hello world looks like. The thing about Rust is you define what the variables are and it enforces them in a sensible way as opposed to C. So you can define a variable I and it will be a default type, but this J is a specifically unsigned 32-bit number. So when you try to set it to a negative value, you'll get an error message, which is nice. Anyway, all right. And so let's take a look at integer overflow in C. This is a common flaw in C. So if I make an unsigned character, X, and then I assign it to a number, 230, which is above 127. It's not a printable ASCII character. And as I mentioned before, this really shouldn't be possible. It doesn't make any sense. That's not a character. But a character in C is an 8-bit integer. It can hold numbers from 0 to 255. So it does. Now I'm going to make a loop from I equals 1 to 10, and I'm just going to keep adding to this character X. And what's going to happen is I've got it here. If I look at my ovc.c, there's the code. And if you run it, I got to shmode it. No, I got to run the not C, the executable. There you are. So you start at 231, you make it bigger and bigger. And when you try to make it bigger than 251, it wraps around like an odometer and goes back to 2. Now, if you really understand C, this is this is going to happen and you don't freak out. But like I say, this is one of the pitfalls. You defined a character, which is kind of mind-bending enough. But even if you understand that a character is an 8-bit integer, so it's an integer, how is it do you add to it and it gets smaller? How are you supposed to know that? That's integer overflow, which is a source of a lot of vulnerabilities. And that doesn't happen in Rust. Here's how it looks in Rust. It's in my directory here, OV app. If I look at this one, let's do an ls. There it is, ov.r. All right, this is how you do it in Rust. I make a mutable, unsigned 8-bit integer, X. It's exactly the same thing as C. Mutable means it can change. If you don't put the mut there, values cannot change in Rust, which is kind of nice, but this is immutable. Now I just try to add to it over and over and over. This is exactly the same thing I did in C. When you do that in Rust, it adds up to 251, and then it stops and says you can't add with overflow. It doesn't just roll around and give you the wrong answer. It stops with an error message saying, wait, you just tried to add that would make it bigger than would fit in the variable type. So it tells the developer something's wrong and they can fix their code. It doesn't just keep sailing through, giving you the wrong answer, creating security problems. So that's why developers like it here. And then the one we've been doing a lot of, the string overflow. So here's a string overflow in C. Let me put this one in. Oops, I got to copy it from inside here. All right, here's a string overflow. There's the code. All right, so I'm going to go up here and then nano strov.c. All right. And then I'm going to compile it. Now you can see in the code here, try making it, I'll do it here where it's bigger. All right, there. So I defined 2 strings that are only 5 characters long. So they have 4 A's and then the null byte that C needs at the end to terminate it. So there you are. And I have the addresses printed here. Now you read a new value for string 2 from the user and just print them again. That's all that happens here. So let's see what that does in practice. I need to compile it and then run it. So I copy that. STROV, all right, fine, I changed the name. So this one is STROV, all right. There, all right. All right, so if I put in CCCC, Then let me try and make this fit more neatly on the screen. There, I had it. There we go. All right. So string 1 is here at 4B. String 2 is at 4.6, stored before 4B, only like 6 bytes before. String 1 contains AAA, string 2 contains BBBB. When I put in CCCC, string A contains AAA and string 2 contains CCCC. So here it works as expected. But as you might guess, if I run it again and I put in more C's, then bizarre stuff happens. I tried to change the value of string 2. Now string 2 contains a whole lot of C's, far more than 4, more than it has room to contain, and string 1 has changed. And again, I invite you to consider the plight of the poor coder. They're trying to write a program. They define 2 strings, they change 1 string, and it changes the other string. And it doesn't have an error message or anything. It just says, well, you're stupid. You were supposed to see that coming. And that's insane. That's superhuman, especially in big complex code bases. It's hard to see that coming. And this leads to the buffer overflow vulnerabilities we've been exploiting. And this is really because C laid a booby trap for you and you fell in it. And this will not happen with Rust. So let's do it in Rust. Get back to here we are. Okay. So in Rust, I'm going to make a directory for it here. I just followed a tutorial that did things the sort of professional way. All right, I'm already in the right directory. So you make a separate directory for each app, which is not really necessary, but it's good when you have large programs. For these little simple ones, you don't really need it. But anyway, this is the code that does the same thing in Rust. I'm going to save it and compile it, which is Rust C -G string.rs. Right, something bad happened. All right. I got string.rs. See these things, Rust C -G string.rs. See what I got? Oh, it did compile. Oh, okay. So here's AAA, here's BBBB in Rust. If I give it CCCC, it appends it to the value in string 1. AAA now contains that, but it didn't change string 2. So that's a little bit strange, but that's not terrible. And if I put in a lot of C's, it doesn't have any problem. It just makes this one longer and it doesn't change the other one. And by the way, notice that the addresses never change. String 2 is always stored. That's because if you go in the debugger, you'll see this address contains a pointer to the data storage address, and that's changing. When you put more in there, it just moves that pointer to some other part of memory that has enough room and puts the string in there. So this is why developers love it. It doesn't drive you insane. If you change string 1, only string 1 changes. Nothing else changes that you didn't intend to change. And so Rust just has a lot of these good things. It also handles dangling pointers and memory leaks better. So, you know, they thought of these various flaws, all caused by the way C handles memory, and they fixed them, which is why developers would much rather be using Rust. They wouldn't have so many mind-boggling catastrophic failures. It would just have bugs and report errors. And when you get rid of the errors, it would actually work as intended. So that's what I wanted to show you. And there's a few Rust challenges there if you'd like to play with that.